Hello, my dear sweet students. Are you ready to get into R? Ha ha, I know you are. All right, let us enter into my computer. So for all these examples, we're going to require Flexplot, tidyverse, and also CalPlot. And by the way, CalPlot just lets you put more than one image or more than one graphic on one page. So let's see here. We've got logistic regression first. Again, that is the most commonly used generalized linear model that we're going to encounter. So here's my research question. It looks like it came off the page here. So, logistic regression. After controlling for minutes fighting, what is the influence of willpower on death? Okay, so this is the Avengers dataset. I don't know that I've ever used this on YouTube. So welcome to the Avengers dataset. So this is a dataset that I simulated about the final battle of the Avengers. And so we're trying to predict, at least in this first question, who died, and is it a function of how much willpower they had and after controlling for minutes fighting. So that's the basic idea. So reading in the packages and tidyverse I'm going to use occasionally to do some data transformations. Not transformations in like log transformation on the outcome variable, but anyway, you'll see in a minute. So what I should be doing more regularly, which I haven't been doing because I've been slacking off, is I should be looking at the univariate distributions first. So we've got those who died in the final Avengers battle. The majority did not, which is good, but some did. Looks like about 100 people died out of, so in like 700 didn't die, so maybe we have about 800 people total. Okay, so that makes sense. Minutes fighting. So we've got a very positively skewed distribution here. It's not zero inflated because the mode isn't at zero, but we have a lot of skewness. So most people, it looks like they lasted about 10 to 15 minutes and then very rapidly died off after that. Not died off in the literal sense, but people just didn't have the stamina, which makes sense. Willpower is normally distributed. It ranges from, looks like negative 0.5 maybe, or negative 5 to 120. If I were looking at this, I'd say, that's odd to have one score below zero. Is that a mistake? And I might do some data cleanup, but I'm assuming this is some sort of a Likert scale, something or other. All right, so now that we've looked at that, let's go ahead and look at a Flexplot graphic. And not surprisingly, well, let's see. Let me just introduce you to some options that you may not have seen before. There's method equals logistic, which will actually in the background fit a logistic regression to it, which is really cool. And we've asked it to give us a ghost line, which is for the middle area of minutes fighting. So it looks like if you are in the low category, so if you didn't fight for very long, higher willpower probably meant you were more likely to die. And I guess that kind of makes sense, that if you didn't fight that long, maybe it's because you died. I don't know. And those people who are high in willpower, yeah, let's go get them, and they didn't fight very long, that may mean that they actually died. That actually kind of makes sense. Whereas if you fought kind of the average amount, there's a slightly negative relationship. So the more willpower you have, the less likely you are to die. That's kind of intuitive, I guess. And then likewise for high, so if you've been fighting for a long time, that probably means you have a lot of willpower. And also, the more willpower you have, the less likely you are to die. So that's kind of interesting. But this is just a plot, so we, of course, want to model it. So if we go down, and right here we have an interaction. Make sure to model that. So yeah, those lines are not parallel. So I'm going to be sure to model an interaction. So I am going to, remember my research question was, all right, once we control for minutes fighting, what effect does willpower have? And so our reduced model is going to have minutes fighting in there, because again, we want to determine the unique effect of willpower. And once I do that, now that I fit it, we can compare fits of the two models. And we get this lovely plot here with our logistic regression. Hey, remember earlier I said the link function curves the line? There's an example right there. That is what the logit does, is it severely curves the line, and it makes sure that you can't get, like underlying all this, you have 1 is no, 0 is yes, or vice versa, one of the two. and it wouldn't make sense to predict that you are more than dead. So it makes that logit function makes sure it stays within the range of what it should. And so, again, normally what we look for when we're looking at compare.fits is how different the predictions are. And so, because the reduced model says that, or doesn't model willpower, it has a flat line, as it should. But now, we're trying to see if the differences, or if the predictions are different. And they are, at least in this one, they're vastly different. But look at this. It's making predictions in this area where we don't actually have data. And by the way, I've already seen these data, and this actually puzzled me because here in a minute we're going to see that the statistics seem to suggest something different, that actually the reduced model is probably better. And I couldn't figure out why, and I realized, all these predictions down here, we're extrapolating beyond the range of the data. So, but if you keep it within the range, the two prediction lines are actually quite similar. So, anyway, there I wrote massive differences in prediction. That was before I did the model comparison. By the way, this is a good opportunity to tell you to update Flexplot. I think it is version 0.8.12 or something that I'm on. So I'm going to update real quick. I'll see you in a minute. My apologies for the long wait. So, now that we've done that, let's go ahead and look at our statistics. And oh, they're just beautiful, aren't they? So we actually have some ambiguity here. So the p-value, if we use traditional 0.05, that tells us that we should go with the reduced model. Because it is not, basically, if again we use a strict 0.05 threshold, it cannot detect a difference between the full and the reduced. And because it can't detect a difference, we go with the more parsimonious of the two, which is the reduced. And also the Bayes factor favors resoundingly the reduced model. However, the AIC slightly favors the full model. And down here we get what are called sensitivity specificity table. So, and I can never remember what these are. But accuracy basically means how accurately, on average, can you predict whether people died. And so both of our models have identical predictions. And let me give you a little background. Like, how can that be? They have different predictors. Well, what happens, especially in a situation like this, when you have the vast majority of people didn't die, often what will happen with logistic regression is it will just predict nobody dies. Even though the coefficients and a bunch of like statistics in the background are different, the actual raw predictions are exactly the same. And so that's what's happening here, that whether you're using the full or the reduced, even though the probability of death might be different, the actual prediction of this person died versus not, they are identical. And so you get accuracy of 87%. Sensitivity is... I can't remember what it is. And I have to look it up every time because I don't use it enough. And so I'm going to let you look that up. Sensitivity, specificity, I'll leave a link in the description. So that's what the model comparison says. So the model comparison generally favors the reduced model. And so I wrote this note to myself. No specificity. Oh, yeah, because... yeah, you will not get specificity values when both models predict everyone lives. Also, the results are a little ambiguous. So the p-values of the Bayes factor and the BIC favor the reduced model. AIC favors the full model. If you look at the visuals, they kind of sort of favor the full model. So what do? I don't know. And if you've seen... actually, I don't know when that video will post, but I will have a video about... how awesome ambiguity is, and ambiguity is okay, and I will link a paper in the description. And I'm okay with ambiguous. It's okay when you can't make a decision because the model is ambiguous. If there's ambiguity, that means that you don't have this resoundingly clear answer. That means your model may not fit very well, and that's okay. We should be cautious in those situations. So at this point, I'm going to favor, well, I put full here. I don't remember why I did that, but I guess it doesn't matter. You get these warning messages. Don't worry about that. Maybe in a future version it'll be fixed. But you get the raw coefficients. So what does this mean? It's really hard to interpret what's going on. But that minutes.fighting basically says for every minute you fight, I think that's why I did the fulls, because the minutes fighting has a slightly more intuitive interpretation than the willpower, and willpower is, and minutes fighting is not in the reduced model. So For every minute you fight, we expect your log of the odds of dying to decrease by 0.12. If you want to see this, you can look in my previous video about, I believe I showed you how to interpret odds ratios and that sort of thing and what all these numbers mean. So if you're interested in that, look at the video in the description. But the more I do this, the more I realize, you know what? These numbers are basically going to tell me what I can see in the graphic here. Why not just look at the graphic? And then I don't have to worry about these log odds and these odds ratios and doing mental gymnastics. I can look at the model. I got the model comparisons. To me, I have the information I need, so I'm good. Anyway, so if I were to make some conclusions, it seems to be, and I'll just look at this plot to make my conclusions. So it seems to be that despite appearances, willpower doesn't actually make a difference. So let's actually go ahead and visualize the full model. So the reduced model, and we'll go plot equals model, because we don't really need to see the residuals. And actually the other thing I'm going to do is I'm going to go jitter equals C0. The first argument is how much we want to jitter the x-axis, which we don't want to jitter that. And the y-axis, maybe I'll try 0.1 at first and see how that looks. So that just separates the data. So basically our model really sucks. Yeah, that's basically all there is to it. Our model sucks. It says that we are not good at predicting who died based on minutes fighting or willpower, I should say. And the best our model can do is predict that the majority of people are going to survive. So, and that can happen sometimes, and that's okay. So that is my regression example. I don't know if I'm going to break this up into separate videos for each of them. Actually, maybe I will do that, just so it's easier for you and it's easier for me. So that is part 1, which is logistic regression. In the next one, we're going to do Poisson regression. So I'll see you then.